Chapter 6, Number 65, the so-called conical pendulum. A toy airplane is tied to the ceiling with a string, and we know its mass. When the airplane's motor is started, it moves with a constant speed, which is given in a horizontal circle of known radius, as illustrated in the figure. Find the angle the string makes with the vertical and the tension in the string. So the key thing here, of course, is that the object undergoes circular motion. So I'm going to draw a free body diagram for the plane. So there's our plane, and we're going to draw all the forces that act on it. And what we have here is, of course, the weight, as always. Draw that first. And then anything in contact with the plane. And here we're going to assume that the air is not significant, although most likely the way the motor works is to drag air through it, like any other propeller. But we're going to sort of neglect that effect and say all of that cancels out, so keep it going at constant speed. The other thing in contact, of course, is the string, which exerts a tension along its own length. So we have something like that. And we're given that the tension makes an angle theta here with the vertical. So I'm going to actually resolve my forces into the standard axes. The standard x is over and y is up. And that means I'm going to break ft into fty and ftx. And I'm going to say, well, I have ft, this is fty, this is ftx, and this is the angle given as theta. And we can see, we've done this game a fair number of times, that ftx is going to be ft sine theta, and fty is going to be ft cos theta. And again, you should walk through this. This is the same kind of thing we've been doing all along. In this case, for instance, ftx is the opposite side, so it's going to involve sine, and fty is the adjacent side, so it's going to involve cosine. You should convince yourself of that rather than just take my word on it. The key bit that's going on here is that our object is going in this circle. And although it's drawn here as an ellipse, they mean it to be a horizontal circle. We know that because, well, they tell us it's a horizontal circle. And so therefore, the centripetal acceleration has to be inward along that circle. So if I take this as being the moment that the plane is coming out of the page at me, then inward along that circle is this way. So there's an AC pointing that way, which gets transposed to our revised diagram that way. And we can actually compute it because we were given the velocity and the radius. So we can say that the centripetal acceleration needed would be v squared over r, which is 4.47 meters per second all squared over 1.28 meters. And that gets us a numerical value of 15.61 meters per second squared. I'm going to keep 4 sig figs, even though I know I really only have 3, because we'll be doing calculations and it's easier to do that later. All right, so then we say from our free body diagram, we have that the sum of the forces in the x direction are going to be just ftx. So the only thing that points in the horizontal direction. And then according to our axes, it's actually a negative. We'll see that's not that important as long as we're careful, but there we go. And then over here we have the sum of the forces in the y are going to be, well, we have an fty and we have an fg, but fg points downward, so we put a minus sign on it. And then from the second law, we have that the sum of the forces in the x direction is going to be the mass times the acceleration, but the acceleration is magnitude AC, but points negatively. And notice that negative sign kind of corresponds with the negative sign from the other expression for fx, so that's okay. We're in a good place. And here it goes in a horizontal circle, so it goes neither up nor down. It has 0 vertical acceleration, so those forces sum to 0. All right. From there on, what we're going to do is just combine these two sets of equations. So we're going to have something like minus ft, and I'm going to put in our substitution now, ft sine theta is equal to the mass times minus AC. And we'd also have that ft cos theta minus mg is 0. Now here's our tricky bit. We want to get theta for part A, that's either of those, and ft for part B, and they are linked in some annoying way. So I'm going to go another board just to do the clever trick you can do here. It is kind of clever, even though it's a little weird. Notice that we do have M, we do have G, of course, and we do have AC. So we have everything we'll need, they're just arranged in sort of an annoying way. Alright, so then we copy the equations over like this, and I'm now going to solve them to make them look similarly. Now you might think that traditionally what we do to solve them is we've been doing things like add the things that have opposite signs so as to cancel out the ft. That doesn't work here because it's not ft, it's ft times something, and it's times different things, so they won't cancel out. Instead, I'm just going to simplify by getting rid of the minus sign and then by bringing mg to the other side, and I get these two equations, which doesn't look like they helped all that much because all I've done is clean them up a little bit. But now I'm going to apply sort of this magic algebraic trick, and I'm going to say if I take the top equation and then I divide it by the bottom equation, then we get some trig magic to happen, because we can say that ft over itself cancels out, and m over itself cancels out. And then, most magically, sine over cosine is always just the tangent. So this becomes tangent of theta equals the ratio of AC to G. You might be noticing that this seems to happen a lot, where tangent of theta is the ratio of some stuff. Really the ratio of things along perpendicular axes, and that is actually quite common. So we can go and get this value, and we can say, let's go up here, we can say that theta has to be the inverse tangent of AC over G, which is the inverse tangent of, this comes out to be 57.85 degrees, which I guess we have, it looks like 3 sig figs, so 57.9 degrees. I think the textbook actually says 58 degrees. Sig figs and trig functions are funky, and so that's probably all that is. After that, we need to get the tension, and we can go to either of these two equations and get the tension, because they're still true, and so we end up with, say, ft is MAC over the sine of the angle we just found. And if we throw in those numbers, what we get is 1.3835 newtons, and with our sig figs, that's really 1.39 newtons. Again, for some reason, the textbook rounds to 2 places, but we really have 3 sig figs, unless Walker's using 9.8 for G, but I think he uses 9.81. So we end up with something like this.